Good morning, everyone. We'll let people enter the room before we get started. I'm joined today by my colleague, Daniel Moyer. Good morning, Daniel.
Good morning, Nathan. Good morning, everyone.
Yes, and as Daniel said, my name is Nathan. I'm one of the trainers here at Briggs & Stratton Energy Solutions, formerly known as SimpliPhi Power. We will be doing a training together this morning on AC and DC coupling of a PV system with our batteries. So there are many existing AC coupled solar arrays on people's roofs, and more people are wanting batteries. And so the point of this training is to make you comfortable with using our batteries together with various equipment from other suppliers to add SimpliPhi batteries in to either an AC or a DC coupled solar array system. So we'll wait just a couple more minutes. It looks like the numbers have stabilized here. So a couple things as we get started. If you are here for the NABCEP credits, this is a NABCEP approved training. You can get continuing education credits by staying until the end and participating in this training. If you have questions during this webinar, feel free to use the Q&A feature of Zoom. Go ahead and drop those questions in Q&A. And Daniel, if I'm going and there's a great question that comes up and you don't answer it by text response, go ahead and interrupt and we'll bring it up for everybody.
Yes, of course.
So welcome, everyone. I hope you're having a good morning or afternoon or evening, depending on where you are around the world. We're going to go ahead and get started now. So again, the title of this course is AC and DC coupling of a PV system with SimpliPhi batteries. So if you are not familiar with SimpliPhi batteries, or we're one of the leading battery manufacturers here in the US, we operate on some principles. One of them is safety. So we use a cobalt-free chemistry. We use lithium iron phosphate, that's LFP battery chemistry. And that's really the safest existing battery chemistry on the market for home backup power. And by eliminating cobalt, we essentially have no risk of unmitigated thermal runaway. So those battery fires that you see where the fires continue to burn because the battery is the source of the fuel, we essentially, by not using cobalt, don't have that problem. Our batteries will self-extinguish, and we publish our 9540A test results, which show when pushed into thermal runaway by external forces, our batteries do self-extinguish. And that's an important point when you're putting batteries in your home. You want the safest battery possible, not necessarily the lightest, but the safest. And a key feature of that is that these batteries also last the longest. We get the most number of cycles out of LFP batteries, and that matters as well for these types of investments. We are certified by external organizations, including Underwriters Laboratory. We have UL 1642 on our cells, 1973 on our battery modules, and 9540 on some of our system level designs. We also interface with other people's equipment, so we're somewhat agnostic to others' equipment, somewhat inverter agnostic, although we are going to recommend some of our best used inverters, including Briggs & Stratton's own 6 kilowatt inverter. We have UN Department of Transportation certification for our batteries, and that allows us to safely ship these batteries to you. We have air shipment approval for some of our batteries, the ones that fall under the weight limit. We are characterized as proven technology. We've been making LFP batteries for backup solutions since 2010, and that might not seem like a long time, but keep in mind that Tesla didn't come out with their Powerwall until about 5 years after we got started. We've been deploying batteries all around the world. We have batteries in over 45 countries, probably more than that, with over 300 plus megawatt hours installed worldwide. That's a pretty large amount of storage worldwide. We have several 100,000 batteries around the world. We are tested and validated by the US Army and Marine Corps. So back in, I think it was 2011, we were approached by them to try to prove to them that lithium battery technology can indeed be very safe, even in rough conditions. And We went through some rigorous testing with them at the Aberdeen Proving Grounds, their testing grounds. We were even deployed by the Army and Marine Corps as well overseas. We have also a business model that demonstrates we care about social impact, and profitability and social impact can coexist. We do support donations to projects. So if you have a great project, feel free to reach out. It has to be towards a nonprofit, but please let us know if you've got something that you think might interest us. We also care about simplicity. We care about solutions that are easy for customers to install. Solutions for that make the job quicker, more efficient, and we try to optimize for any generation source, including we have our batteries installed with wind, solar, even hydro, micro hydro, on or off the grid. So our batteries are off grid. I know there are plenty of manufacturers that only want to warranty on grid options. We have off grid solutions as well, with carrying that full 10-year warranty for us. Our solutions allow us to store battery for critical backup power. As you know, that's probably why you're here. We maximize resilience and energy security by giving people that backup power from when the power goes down, when those outages occur. It's happened to me a few times this year. We in California here had flooding this winter, and I lost power for some time. And as well, we get occasional shutdowns for fires, as many around the world experience different events like that. So having even a small battery backup system allows you to maintain that internet connection. It allows you to maintain working, etc. Garage door opens, all those kind of things that are important for homeowners. So there's also ways, of course, to create savings on utility bills with LFP battery chemistry. You can get 10,000 cycles out of these batteries once per day. That would be 27 years, right? So you get there's a lot more that you're getting with current LFP batteries compared to those old lead acids where you might get 1,000 cycles out of them, and really have limited depth of discharge. You get a lot more out of lithium batteries. They're really the only solution I would consider using, and I do have them here in my house. So we will go ahead and get going. I'm not going to speak too much about this slide. I just want to point out that 2 years ago, SimpliPhi Power was acquired by Briggs & Stratton, and we now have a complete energy solutions division offering generators, batteries, inverters, gateways, you name it. We're there to offer even high voltage solutions to our customers. So if you have a very large project, maybe more than a couple of dozen batteries, you might consider going to a high voltage solution. And by elevating the voltage, going to up to 1200 volts, going to 1000 volts, what you can do is come in with smaller cabling, reduced cost, because you're going, you're using less current. These are typically 3-phase applications. And SolArc has come out with a 30 kilowatt inverter. Yes, a 30 kilowatt inverter as well as a 60 kilowatt inverter, and we have battery solutions for those inverters that are about to be released. Next week, Daniel will be giving a talk on integrating generators in with ESS systems. Daniel, do you want to say a few words about that before?
Yeah, looking forward to it next week. After the holidays, we'll be giving that presentation. And really quickly, what you're seeing there in this kind of the bottom center is one of our Power Protect 10 kilowatt, either propane or natural gas generators. And these fit perfect for pairing with inverters. They're not too big that the inverter can't handle all the power, but they're big enough to properly provide a good charge on the batteries. And this is one of the smallest footprint for that class. So looking forward to seeing you all next week.
So Stephen asks, Stephen mentions Fronius inverters do not play well with other inverters, I've been told. We will get into talking about inverters towards the end of this talk, especially as we talk about AC coupling designs. I don't have a lot of experience with Fronius. Daniel might have more than me. So let's jump to that at the end. Bernard says, how do I purchase for resale in Freeport, Bahamas? Bernard, feel free to send us a message afterwards, and we can put you in touch with our sales division We certainly have, in fact, it's funny you mentioned that. Just this morning, I was seeing there were 36 batteries being installed in 2 of our boss cabinets in Bahamas. And all of us were volunteering to go down and help supervise that project. So we definitely would love to be in touch with you about distribution in Bahamas. Michael is asking about the 10 kilowatts. I think he's asking about the Power Protect. He's asking, is it AC or a DC? This is an AC generator. We can get into that a little bit later in the talk as well. Especially next week, we're going to be going through generators. And so if you're interested in how generators can be optimized by use of battery storage, turn that generator on, run your loads, but also charge up your battery system and then shut that generator off. Daniel's going to be going through all of that next week. So if you haven't signed up for that talk yet, that training yet, I highly encourage it. So again, we've got distribution points all around the world, and we encourage you to reach out as one of you just did. We have a lot of different products on the market. What you're seeing here in the top left corner, you see our access cabinet. That is a cabinet that comes with an inverter already installed, already programmed for you. It's a very nice plug and play solution, nice clean look. NEMA 3R outdoor rated enclosure. And it's got cooling fans that are temperature regulated and built into it. That same cabinet can be used to house up to 12 batteries. When we put only batteries in it, we call that a Boss 12. That comes in a smaller format as well. It's not pictured here, but it's half the size at a Boss 6 cabinet. A lot of customers are wanting to keep those batteries safely inside an enclosure. Our enclosures are outdoor rated. High voltage is shown on the right side of the screen here. And again, I mentioned we're going to have options for a 30K and 60K kind of plug and play solutions with the larger the 30 kilowatt and 60 kilowatt solar converters that are coming out, a company in which we partner with on a lot of our products. In the bottom, you can see the different batteries that we offer. On the bottom left battery there is one of our PHI batteries. In the middle, it's an SimpliPhi battery with more advanced BMS offering closed loop communications. And the battery on the right is our SimpliPhi 4.9 kilowatt hour battery. This is a wall mountable outdoor rated battery. NEMA 3R, it does have a conduit box that can cover the top as well. And so this battery is a nice, easy to install battery, has that same advanced BMS with a closed loop communications. And so here's a kind of more complete lineup of the batteries showing those cabinets as well. And so one nice thing about buying smaller format batteries instead of buying one large batteries, you can expand your system later on. Maybe you, the homeowner, or you, the installer, are limited on budget, and so you can start off with a small system and add to it as energy needs advance. One of the things that Daniel and I find, and in fact myself, as I've gotten into a solar system, is that once you realize that the solar energy is free, you start adding and converting more and more of your appliances to electric. So one of the things I'm looking forward to doing in my condo is switching my my natural gas heating system over eventually to a heat pump system, a mini splits, or several mini splits most likely. But there are many things that customers do like that, and so having a smaller format battery offers that expandability in the future. You can always add more batteries. The system generate that free energy during the daytime and discharge at night. This didn't make sense a few years ago before LFP batteries came out, right? The lead acid batteries were just too expensive as a storage mechanism. With the long lifetime and a large depth of discharge you can get out of LFP batteries, these are now good options, even for just saving money, let alone backup power. So what's driving all these battery installs, right? So more and more people are working from home. Daniel and I are both doing that. I'm broadcasting to you from my dining room. Home as a haven, right? So people are working from home. People are spending more time at home, and they want their home to be able to be maintained. They want their air conditioner to be able to stay on, their internet, etc. And so that seemed to increase rapidly during the pandemic, of course, but it seems to be a trend that's not going away. Of course, we also are all well aware that we have infrastructure that's aging. So we have infrastructure in California that's subject to fires. Around the world, infrastructure is, aging and maybe not being replaced as fast as the growth of electricity demand, right? And so in the coming years, especially as more and more things go electric, it's going to put more and more strain on the grid. And I guess it was just a year ago or 2 years ago that they had these massive power outages in Texas, and systems failed. And so having battery backup power can help customers when infrastructure does fail. And of course, I don't want to underplay vandalism as well, right? There was a case where someone recently shot out transformers and was able to bring a whole section of a grid down, right? So these kind of things can happen. The wars around the world are showing that attacks on infrastructure also can cause power outages. Of course, climate-related disasters are well known. I went to a graduate school in Florida, and my first few months there, I had 2 one-week-long outages due to hurricanes, and lost a lot of food in my fridge during those weeks. Then, of course, a big driver is electrification of everything. Out here in California, we have loads and loads of Teslas. It seem to always be passed on the highway by Tesla, but we have plenty of Rivians out here. Ford's come out with their electric pickup truck, the Lightning. There are lots and lots of electric vehicles on the road. And that trend, I do not think is going away. Those who are buying electrics seem to be quite happy with them. And I'm looking forward to moving to one myself eventually. And of course, more of us want clean energy solutions, right? We like being able to use clean energy, renewable energy. The solar panels on my house allow me to not feel guilty about the hot tub that they're running outside right now, which draws 150 watts continuously to circulate and 4,000 watts when the heater's running. Excuse me, I didn't mean to move the slide just yet. So one key fact I want to introduce here before I leave this slide is there are a lot of solar owners around the country, many solar installations around the country. Only 15% of these solar owners right now have battery storage. 61% of them want battery storage. That alone, right, is a big driver, right? People that have solar on their roofs are people that might likely become customers of for battery solutions in the future, and are an easy target for identifying somebody that might want to do business with you if you are dealing in batteries, if you're an installer.
Hey, Nathan, sorry,
yes,
Daniel here. Just go back one slide. One thing I did want to point out, there's a lot of new ITC, and the new IRA has really opened up a lot of opportunities for us. They have extended the 30% tax credit into 2033. And further, now you can leverage this tax credit without having to install solar. The idea that you can also just install storage without solar is a huge thing, especially when we're talking about maybe adding storage to a generator home to reduce runtime and save fuel as well. Another opportunity is this direct cash payment now available, where we can start to target nonprofits and other entities that couldn't have otherwise leveraged that tax payment. So really excited about some of these energy solutions and policies that are going to help us drive our industry forward.
Thank you, Daniel. That's a great point, right? There are tax credits out there for many things, even just installing something as simple as a heat pump water heater, right? There's credits up to, I think, $3,000 you can get back on that. So our government has realized that, at least in the US, right, that energy security is important, and there are incentives to help move energy security along. So great point, Daniel. Thanks for bringing that up. There are many different ways to use batteries, and I'm going to highlight just a few of them that our customers will often install batteries for. On the left side of the screen, we've shown you peak shaving, and what you're looking at there is the the demand of a customer throughout the day. And so this customer may be in a jurisdiction or a location where the utility is charging based on the demand. And if you go into a higher tier, you can get what are called peak charges, right? And these peak charges can be quite costly. I talked to somebody at NABCEP conference recently who was running a farm, and based on some of his demands, he was looking at $600, $700 a month if he crossed into a certain threshold. So by having batteries, you can use, and people don't always understand this, you can use battery and utility power simultaneously, right? So if you are, approaching that, looks like a 65 kilowatt line where you want to stay under, but you need to hit 70 for a little while, you can use batteries to offset some of that power need that you have. And so that's called peak shaving. In the middle of the screen, there's a display showing a cost per kilowatt hour, and it's based on timing. So this is something that I experience here in California. Cost of electricity overnight is much cheaper for me. The rates go up depending on the demand. And so between 8 and noon, the electric rates are much higher than they are before 8 a.m. And then from noon to 6, these aren't the exact times that I experience, but noon to 6, the rates are higher. In fact, for me, I believe my highest rates are from 5 to 8 p.m. But when people are using more electricity, the cost goes up. And so the electricity companies charge more during those peak demand hours, and you can use batteries to offset these costs as well. You can charge up your batteries when you have lower costs. You can utilize that energy at the time when electricity is more expensive. And you can do this even with a small system to help offset how many kilowatt hours you're drawing during those high rate times. On the right side of the screen, we're looking at integrated solar and storage. So if you do have a solar system, you're well aware that it's only generating power at certain times during the day, and it peaks out when the sun is higher in the sky, depending on the orientation of your array. But so you're generating electricity during the day when that solar energy is coming in for free. You can save it up throughout the day, and then when you get home in the evening and want to use that energy to cook your meals, to run your heater, to run your air conditioner, to run your appliances, maybe you're doing laundry when you get home, that energy is saved and then used later in the day. So these are typical reasons people choose to have batteries, and of course there's off-grid customers as well that we're not showing here. There are some basic definitions I want to get into. One of those definitions is just on how we are coupling. So when we say how solar panels are coupled in PV systems, what we're talking about is how they're connected to a battery bank. So my solar array happens to be a DC coupled array. That array is coming into MPPTs, which take the DC coming out of the solar panel and direct that DC at the appropriate voltages and current rates into my battery. And so I'm going from a DC out of the solar panel to DC into the battery. AC coupling exists, and that's because solar panels themselves produce DC, but when you put a micro inverter, and we'll talk about those, on a PV panel, the PV panel is then converting that DC power of the solar panel directly into AC, usable AC, at the panel level, and that gets fed into the power of the house, the service panel of the house, and can be utilized or sent back to grid. But if you add batteries to that system, you'll need to be able to convert that AC power coming from that solar array back into DC for battery charging. So that's what an AC coupled array is. And so when people are talking about AC solar panels, what they're really talking about is solar panels with microinverters built into them. DC coupling, again, I mentioned that already, but that's just taking the DC from the solar array and regulating that DC to charge a battery bank. AC coupled batteries, some batteries have built-in AC to DC inverter converters to allow the battery to import and export AC. So when somebody talks about an AC battery, the cells themselves are DC, but it's got a built-in inverter converter with the batteries itself.
Nathan,
Daniel.
Daniel here. So one definition, you know, I've been hearing kind of historically is an AC solar module. Now, when we did a SunPower, it was a DC panel, of course, and then they had pre-installed a microinverter on the panel. They kind of glued it to the back sheet, and when you had it out in the field, you'd kind of pop the microinverter up. So that was an interesting definition that I've haven't really seen kind of catch on too much, but an AC solar panel essentially is just a pre-installed microinverter on a solar panel. Just wanted to throw that out.
Thanks, Daniel. Are there any questions yet that we should address?
We have a couple about the warranty. Drew is asking, does our battery inverter pair well with an existing Enphase system?
So that's a great question. We have tested our battery and inverter with the IQ7 pluses and have it functioning properly without any issues. I'm not sure about the IQ8s, and I think there might be some existing testing that needs to be done before we can confirm that they do work with newer Enphase systems. So that's a great question. Are there others we should answer at this moment, Daniel?
No, let's keep going.
Okay, so let's start off with DC coupling. This is the one people are most familiar with. DC power comes from a generation source to batteries, right? And this is almost the majority of our installs, right? Probably 95% of our installs involve DC coming from solar panels. As I said, you know, there are other generation sources that are out there, but DC coming from solar panels is most common. You can keep that example in mind if you'd like. And so if you're going to use DC from a solar panel, there are a number of things about it, right? It's a varying voltage source. It's a varying power source. It's not a constant power. A 100-watt panel almost never exports 100 watts, right? It's most often exports different power, which depends on the current illumination of the panel, shading on the panel, temperature of the panel, etc. And so you need charge controllers, you need devices that are capable of regulating the voltage coming out of the panel as well as the amperage so that we charge our batteries at the appropriate rate. And we can even optimize the power out of those panels with devices we'll talk about called MPPTs, maximum power point tracking devices. Older panels, sometimes, especially with smaller systems, would use a low-cost PWM type controller, which is pulse width modulating. I'll talk a little bit about pulse width modulation during this training. There are a lot of arrangement considerations for PV panels. You want to make sure that you're not going to have shading issues with your array. You want to decide how many panels to put in series, how many you're going to have per string, how many of you are you going to have in parallel. When you parallel your panels, you're going to increase the current. When you put your panels in series, you're going to increase the voltage, and there are limitations with equipment. So you have to design those arrays consistent with the equipment that you'll be using. There are ways to test something called the open circuit voltage. So you get the maximum voltage out of a panel when you are not drawing any current out of it. So that panel goes to kind of a maximized state in which you'll get the highest voltage out of the panel. We call that the open circuit voltage of the panel. If we close the string of panels, so we have one big loop, and you can do this with panels. You would never do this with batteries, but you can do this with panels without damaging them, right? You'll get something called a short circuit current. That's essentially where you have zero load on the panel or very low load. You just have the load of your wire connecting the loop, and you'll get something called a short circuit current. That's the maximum current your panels can output. Of course, current times voltage is what gives you power out of your panel. So if you reduce the current a little bit with more resistance, you'll get a lower current but a higher voltage, right? And what the charge controller equipment does is it maximizes that product of current times voltage. And so when your panels are actually operating at optimal conditions, they're operating at a voltage that's the maximum power point voltage, which will be less than VOC. And they're operating at the maximum power point current, which will be less than the short circuit current, ISC. The lower the temperature, the higher the voltage you get out of your panels. And so you'll get more power out of your panels when they're not as hot. You'll get more power out of your panels when they're clean. And you'll get more power out of your panels if the wind is blowing, because the temperature of those panels will go down. You'll also get more power out of your panels when the sun is more directly overhead, and when there's the greatest amount of what we call the irradiation, sunlight striking the panels. So atmospheric conditions can influence that. I'm not going to talk about how solar panels produce electricity, but it's not a particularly complicated process. It involves something called a PN junction and a differently doped silicon. And the top layer is a transparent layer. And basically what happens is that those two layers like electrons differently. There's and so you get this buildup of electrons on the n-doped side of the solar cell. What you're seeing there, a single solar cell, I'm highlighting it with my mouse. You're seeing those lines that are on those the solar cell. Those are actually connection points, and those are carrying the current. And so if you look closely at a solar module, you'll see those nickel strips going above and below the panels, connecting, above and below the cells, connecting those cells in series. And typically they'll run through a big kind of snake around the panel. On the back, there's something called bypass diodes to allow, if there's shading on a section of the panel, to allow current to just bypass that section of the panel. Solar modules are strung together, and I've been calling them solar panels. I guess technically I should be calling them solar modules. Solar modules are strung together in a system to create what we call strings, and so that's many panels in series. On the left side of your screen is something called a PV diagram, or a current voltage diagram, an IV curve for a panel. An IV curve for a panel demonstrates the current and voltage profile that you would see coming from the panel if you were to vary the load across the panel. Now, this changes depending on sunlight conditions, etc. So you could have many of these curves depending on what the current condition is, what the current temperature is, etc. So one thing to point out, when there's more sunlight, current increases. It doesn't really have much of an effect on voltage. When there's lower temperature, voltage increases. It doesn't have much of an effect on current. So temperature causes the panel voltage to go up, illumination or the amount of sunlight causes the short circuit current to go up. And this graph shifts up or down accordingly, left or right accordingly. Of course, the maximum power point is the current times the voltage, where we maximize the area under the curve. And you can imagine drawing a rectangle under the curve where you get the most amount of area. That would identify your maximum power point. That changes with time as the day goes on, as the demands on the panel change as well. So DC coupling, we need things called charge controllers. And what these charge controllers often do, most of these, I see a morning star there, most of these try to track that maximum power point on the panel. They do that, and they regulate the output to the battery bank. And we have to be careful when we're charging batteries. We can't just dump all the energy into a battery in 5 minutes, right? That battery would overheat. It would cause a loss of capacity of the battery, would ruin the battery. And so we have to regulate how that charge makes its way into the batteries. We have whole trainings around charge, discharge, state of charge. And so if you're not familiar with that, feel free to look at some of our trainings. We have trainings that you can do online through the Power Academy with Briggs & Stratton. We also have webinars, featured trainings like this one, which can tell you about how our systems should be charged, how our batteries should be charged. So maximum power point tracking, bottom left of the screen, there's a couple of ways to maximize the output of a solar panel. One way is by maximum power point tracking, and what this does is it regulates the load on the solar strings in a way to increase the output power of the panel. So you can imagine if you draw too much current, the voltage drops too low. If you don't draw enough current, right, you're not getting enough power out of that panel. You get a high voltage, but low current means low power. And so by varying the load on the panel and sending that that power from the panel to the battery, we can vary how much power we're bringing off the panel. And what it does is uses an optimization strategy to try to stay at that maximum power point. A PWM controller, we're going to get into that a little bit more on the next slide. But these are a little bit less efficient, and what it does is kind of pulses many times per second the current draw out of the panel to try to keep that panel at the optimum voltage. MPPT controllers can be very efficient, up to 99% efficient. So what that means is 99% of the energy that they're drawing off that solar array, they can direct accordingly. The other 1% ends up as heat, which is why you see those cooling fans on the top of that MPPT controller.
And Nathan, what I'm seeing a lot, Daniel here, is a lot of times what you showed that Morningstar, or here's another SunSaver charge controller, is that these used to be historically external devices. You would have a separate charge controller, a separate inverter. Now, especially with the coming out with our ESS inverter, is that it's all in one. And a lot of times these MPPT charge controllers are built into one box with the MIDIs, the micro interconnection devices, as well as the inverter, as well as the charge controller.
That's a great point, Daniel. And yeah, so our solutions, of course, and more solutions are basically putting together the charge controllers. They're putting together the inverter. They're putting together the MPPTs and putting them all in a single device. And our device is a good example of this. These devices are known as hybrid inverters. They also give you the option to feed back to grid and communicate with external devices. Most of these are app-ready devices. Ours is. I use my app to check my batteries last night at 9 p.m. Right, these are smart systems, and more people are wanting to have systems where they can monitor remotely as well. So let's talk just a little bit about what a PWM controller would do. So recall what I said earlier, that a solar cell essentially pushes charge to one side, and if you start to draw that charge off, the voltage goes down. If you draw too much charge off, the voltage will essentially go to zero, right? And you'll get a short circuit condition. You get the maximum amount of current flowing through your loop, but no voltage, you get no power. And so by drawing little bits of current and regulating how much current you're drawing for over a short period of time, so this window of time that I'm showing on the screen, that's a very small window of time. These pulses occur many times in a second. So by pulsing, we can approximate the voltage that we're seeing. We can approximate a lower voltage than what that open circuit voltage of the panel is, and maximize the output of the panel that way. Most newer systems are not using this technology. It's a little bit less efficient, but you'll still see some lower cost charge controllers out there that do pulse width modulation. More and more are doing what I was describing earlier with MPPTs, and the maximum power point tracking shows the way that this panel is trying to optimize power. Notice that if power is current times voltage, current is on the vertical axis and voltage on the horizontal axis. If you pick a point where there is no voltage, where the current is maximum, like the short circuit condition, you have no area under that section of your curve. If you start to increase the current, decrease the current very slightly that you're drawing out of the panel, the voltage starts to go up. And you notice that since voltage, right, times current gives you area under the curve or power, you'll see the power start to increase. So as you draw more and more current, the voltage stays relatively constant. It drops slowly, and then in the end, we hit something called the knee, and the voltage will drop off more quickly increase more quickly, and the current drops off quickly here. And so this point is the maximum power point. It's the maximum area you get under the curve. Of course, that red curve changes constantly throughout the day as the panel heats up, as the panel cools down, as shading comes in, etc., based on array conditions. And so your MPPT is constantly making these little adjustments. It'll draw more current and see the voltage go down, so it'll draw less current, see the voltage go up. And so you're kind of, the job of the MPPT is kind of to move around on this maximum power point, and just make sure it's at the top of the hill there. It's the most power you can get out of the panels. What I've shown here is a midnight solar charge controller. Again, as Daniel said, many of these charge controllers are just built in. We've got 2 of them independently that operate inside our 6 kilowatt inverter that we'll show you a little bit later. So if you are doing a system design, what does a DC coupled system look like? Well, you'll have an inverter, what we're showing here, some Victron equipment. You've got a grid, and that grid can come into the inverter. That inverter can communicate with a charge controller. This is a smart charge controller here. Victron has an app that you can use to regulate your charge controller and your inverter. The charge controller will bring the solar array in. The connection, the power connection between the charge controller and the inverter is through the DC bus. And so we land our batteries on the DC bus. The charge controller there lands on the DC bus, and the inverter lands on the DC bus, and then your loads come out of the inverter. And so this is a very typical simple DC coupled design. Daniel, are there any questions at this point?
Yeah, we have a couple. You know, somebody mentioned that it was Paul. We talked a little bit about microinverters and AC coupling microinverters to an energy storage system. And he brought up a good point that there are a lot of systems that don't have microinverters. I'm thinking of old SMA string inverters. So just maybe talk a little bit about how string inverters are common, and we can still AC couple as well.
Sure. So I want to make sure that I understand what you're asking. So yes, many of the arrays that are existing, both roof-mounted arrays and ground-mount arrays, consist of DC panels. But I wasn't sure that I understood the question about the inverter.
I think it wasn't so much of a question as just a statement that we wanted to make sure we're clear here, is that the opportunity to AC couple energy storage systems isn't just limited to microinverters. In fact, there are a lot of string inverters out there that are living their lives that we're easily able to AC couple to. Another question, in your DC coupled example, Dylan's asking this, is there any maximum power point tracking done by the inverter, or is it all done by the charge controller?
No, that's what the charge controller is there for, right? So the charge controller is there to maximize the output of that solar array. I guess in terms of what you do with that power coming out of your array, there are some settings in your inverter, right? If you're in a location where you are able to feed back to the grid, you could set your system up so that the power that's coming into the batteries, let's suppose the batteries fill up, you can still use that inverter to draw power out of the panel and send it back to grid or send it to loads. But that's an excellent point that I want to kind of point this out. And I've used this example and tried to push this example with Daniel in our trainings, and that's that you can kind of think of solar panels as rain capture devices or water pumps. And essentially, if there's nowhere for the energy that that's striking a solar panel to go, then that panel is actually not producing any energy, right? The power is available if you have somewhere for it to go, right? So power is a measure of the rate of use of energy. Energy itself, you can think of like water. And if you don't have anywhere to send that energy, if the batteries are full and you can't send it back to grid and you're not using it in your loads, then your 10 kilowatt solar array will be producing 0 kilowatts, right? And so that's a good point. And Daniel, would you like to comment further about how some inverters can send back to the grid and kind of maximize production in that fashion?
Yeah, you're absolutely correct. And I'm also thinking a little bit more about new net metering agreements as well, where we have to definitely capture some of that energy and store it rather than feeding it back to the grid. So the design and the programming will depend heavily on what net metering agreements and interconnection agreements you have available. Let's do one more question, Nathan, before we move on. I'm not sure if I'm getting this. Jeffrey's asking, what is the DC source circuit on a DC module with a field installed microinverter?
What is the DC source
circuit. So maybe Jeffrey, let's.
I think.
Yeah, go ahead.
Well, I will say this: the microinverter is essentially an MPPT tracker that has the inverter built into it, right? So the DC source circuit is the panel itself. So the panel produces DC. That's all it can do. And in fact, each cell on a panel produces, as long as you've got silicon panels, just over 0.6 volts in an open circuit condition, right? And so there's DC coming out of a panel. That's all that the semiconductor PN junction can do. That's what it does. But once that comes into the microinverter, that microinverter is responsible for moving that energy from DC, converting it into AC, and pushing it out to the system, to the loads of the home, and then if the agreement exists, back out to the grid.
Yep, great. I did say one more, but let's do one more. I think this is kind of the fundamental question of this presentation. What is the best solution to use and charge a battery? Is it DC or AC coupling? And I'm kind of jump ahead and I'm gonna say there is not one best way, but I'll let you take it.
Yeah, I think that there's an argument to be made on both sides. I'm kind of on the DC side of things because every time you switch from AC to DC, there's heat generation and power loss. There are considerations. AC panels, by joining panels together in parallel in AC, you don't have strings of panels that can cause losses on the rest of the panels in the string. So when you have a string of panels in series, the current through any one panel of that string is limited. The current of that string is limited to any one panel's minimum current. However, that being said, panels have bypass diodes built into them. So you can lose some voltage, but that current can still move through the panel, be pushed by the other panels. So a lot of people will say that AC panels perform a little bit better when shading considerations are there. There are also things called DC optimizers. And so I'm biased to think that DC coupling is better. That's typically what's done on large scale commercial arrays as well. But there are arguments to be made, especially for the simplicity when you have good interconnection agreements, to just go with AC panels on your roof. That being said, if you have AC coupled solar and you get a power outage, that AC coupled solar is not available. Even if you have a 5 kilowatt array on your roof, if it's not seeing a grid signal, those panels are not producing power. So adding a battery backup system in which you AC couple the battery system into that existing AC array, then you can have backup power. So it's something to keep in mind that, anyway, I'm on the DC side, but I think Daniel makes a good point. There's no one best solution that fits all needs. So this, I'm just pointing out the DC bus there. This is a kind of a bad example of a bus, but there are lots of different buses that you can buy. Make sure it's rated to the maximum output of your batteries or whatever your limiting device is, and your fuses. So what we're showing you here is a DC coupled design. So you see the solar panels on the left, those are rapid shutdown devices there with the panels. Those are required for roof mount arrays. There's the green thing in the middle of the screen there. That's a signal transmitter for those. Those are Tigos, right, Daniel?
Yeah, those are Tigos. They look like the F, TS4F. I don't believe those have the optimization in them. Okay.
So some of the rapid shutdown devices have optimization, which can bypass certain panels under shading conditions. These typically for the rapid shutdown devices, you're looking at about $30. If you're getting the optimization, it can go all the way up to $100 per device. Some of these devices will take several panels in, 2 panels, but there are power limitations and current limitations on the rapid shutdown modules. The transmitter that's there that I was mentioning sends a keep alive signal through the PV wires. And so it sends a signal, and as long as the panels are receiving that same signal, those rapid shutdown modules act as closed switches. As soon as that signal disappears, somebody hits the rapid shutdown button, or for any reason, if that transmitter stops transmitting, those rapid shutdown modules open circuit and the panels stop producing power. And the reason for that is safety. We want to be able to shut off your solar array in the event of an emergency. Let's give you a simple example. My house has a solar array on the roof, which the strings are coming in at 480 volts. If there is a fire, right, it can easily melt the PV wire housing that's there, and you could have exposed wire. And so for firemen, for safety reasons, for many reasons, right, we want those panels to be shut down at the panel level, at the panel location. So what else do you see in the screen? You've got a critical loads panel in the top. You've got grid coming in on the top right. And this is an example in which we have a large battery backup with a very large combiner down there. There's 2 Boss 12 cabinets. This is solar 12K, Daniel? Looks like
Yep,
a 12K to me.
Yep, it looks like that.
And so you've got a lot of backup power in this particular example. This is a very large battery bank. So let's talk a little bit about AC coupling, and we'll get into some designs for that as well. So with AC coupling, you've got AC power coming from your power source, and that we say roof here, but that could be typically AC couples on roofs. You've got micro string inverters that are producing basically a PV inverter. PV arrangement considerations here, you need to make sure when PV coupling, when coupling these panels, that we're not charging too fast. The charge controllers don't have as much control when you have microinverters producing AC power as they do with MPPTs. And so we need something to convert that AC power coming from the panels into DC to charge the battery bank. We need to be able to shut those systems off as well, right? So let's suppose our batteries become fully charged, and we want to throttle back the power coming from the PV array. And there's something called frequency shifting that can be done to turn off those microinverters. And so those microinverters are expecting to see a signal coming from the power source right at 60 hertz. And so if we use our inverter to shift that frequency, we can turn those panels off. Daniel, could you talk a little bit more about frequency shifting and how that's used to regulate panels?
Yeah, of course, Nathan. So a lot of grid-tied string inverters are looking at the frequency of the grid. And what can happen is that if we need to, say, with the charge controller, it's easy to shut off the flow of energy into the batteries by using a charge controller. But what we see, though, with say a string inverter is that we have to somehow, when the batteries are full and we can't say feedback to grid, we have to somehow curtail the AC charging. And how we do that is by adjusting the frequency of the AC sine wave. And the inverters, the microinverters or grid-tied inverter recognizes that shift and then can start to curtail its charging rate. And then, Nathan, that kind of brings us into a question that we're getting is how much PV can we add to an AC coupled system?
So our batteries are rated at a C/2 rating. And what that means is the batteries can, I guess the easiest way to think about this, and the way we always explain it, is that the batteries could charge up from a state of 0 charge to a state of 100% charge in 2 hours. You don't want to be charging faster than that. So for our 3.87 kilowatt hour batteries, right, we're looking at about 1.9 kilowatts per battery. If we charge faster than that, we can damage the batteries. And so if you had, let's say, 3 of these batteries, you're looking at about 5.7, 5.6 kilowatts of power. right? And we have some examples where we can do this, but you want to make sure that you're sizing your system appropriately when you're AC coupling to string inverters or microinverters. So let's look at an example. This is just a simple string or grid tied PV array, right? So we've got IQ7 pluses, looks like they're attached to solar panels, and those are producing 240 volts of AC power, and that's coming into a loads panel and then being fed back to the main service panel and into the grid. We want to add battery backup to that, and the same goes with a string inverter, right? We're looking at trying to retrofit this array, and in order to be able to use that AC power, it's like charging from a generator, right? We need an inverter to be able to take that power in and feed it back to the batteries. And so here's an example where we're using an access cabinet with 6 batteries, 6 of our 3.8 kilowatt hour batteries there, and a solar inverter to be able to charge the batteries and use that power and then feed that excess power back to the service panel for loads and to the grid if excess power is existing. Daniel, you want to say anything more?
No, I would say a lot of times that that little load center we have there in the middle might be an IQ combiner, either an IQ3 combiner. So you might look a little different on an base system when you walk out there.
Sure. And Daniel, let's talk for a minute about this array. So previously we're showing an array here where we've got solar, right? What happens when the grid goes down? Do we have any battery backup, or do we have any backup? Can we use the power coming at least out of these solar panels to maybe run some small loads in the house if grid goes down?
No, with those being the IQ7s, no. Those are constantly looking for grid. They have anti-islanding protection built into them. So as soon as they see grid loss, they're going to shut down so that you're not accidentally backfeeding the grid when there's an electrical lineman down the road trying to get the power back on in the neighborhood.
So one of the advantages of this system is if the grid goes down, do these microinverters stay active?
So exactly. In this example, we have a solar that's creating a grid that the microinverters can recognize. And the transfer is so quick that the microinverters don't really see that loss of grid. They think that the grid is still there. The solar or our SimpliPhi inverter can now isolate us from grid and provide that microgrid for our homeowners.
Right. So this solar is grid forming. Our inverter, our SimpliPhi Briggs & Stratton inverter is grid forming, and it can keep these microinverters alive. So not only do you have your batteries to power loads when the grid goes down, but now you can also utilize your solar. Right, so you're kind of getting two things. You're not just getting battery backup, you're getting the ability to use your solar when the grid is down as well. And for an extended outage, that could be very important. You now have a renewable source to be able to charge up your batteries that you have access to with the grid down.
And going back to a previous question is that, what's better, AC or DC coupling? And really, when you were to come out to somebody's home that already has these solar panels, already has these microinverters, already has that IQ combiner on there, let's go ahead and leverage that existing system. Of course, we understand that DC coupling is more efficient. That anytime you switch between AC and DC, you lose something. But the last thing I want to do is send a crew up on the roof to remove all these microinverters and then rewire the entire string. Let's leave it the way it is. Let's go ahead and AC couple and not even have to get the ladder out and be on our way.
And that's why Daniel is saying he's not jumping into a camp there, because the best solution is what is most cost effective and most labor effective for the customer. So if they already have an existing system on their roof, keep that system, keep it simple, stay off the roof, right? Just come in and provide a solution such as this one. So there are a lot of examples. I realize that I'm kind of running low on time. There are a lot of examples for DC coupling with off-grid systems as well. And for our batteries with an off-grid system, you can float the batteries in the charging cycle. And again, we have whole trainings around how to float those batteries, or if you should even float the batteries. The charge cycle itself does something called a bulk portion of the cycle, And then there's an absorb portion where we're topping the batteries off, and float is just to keep those batteries at 100%. We don't recommend doing that unless you have a renewable source. And if you do float our batteries, please do so with the 48-volt batteries at 54 volts. So I'm going to kind of jump through these slides here just because I want to get towards the end. Here's that example of a Fronius with, you know, existing AC coupled design. I'm sorry, we don't have time to go through some of these more. Talking a little bit here about rapid shutdown for a DC coupled system. When the solar's on the roof, you're required to have rapid shutdown modules on the roof. For an AC coupled system, those microinverters act as that rapid shutdown, and so they have that compliance there for you. Here's an example where you've got the DC coupled with the rapid shutdown modules there. You've got a DC disconnect as well down at the wall. Most likely this is outside the house. Rapid shutdown button as well. Again, we looked at this example before. Here's another example with a Schneider 6848 inverter there. And you're looking at a similar system with large backup with AC coupled. So I want to point out that there are many different situations that you have to take in consideration. When you are looking at AC coupled, be sure to be careful about sizing your charging equipment and your battery bank accordingly, right? So SimpliPhi products are some key features of our products here. I want to highlight, we use lithium iron phosphate. We use the most expensive but the longest living form factor as well. Our batteries are cylindrical cells. And those last a very long time. It's how we're able to give this a 10-year warranty, which I'm going to hint at right now is about to increase on our communicating batteries significantly. We have UL listings, and I've highlighted those at the beginning. If you need those for meeting building codes, fire codes, and are having trouble with inspectors or AHJs, we're happy to provide you any of the documentation that you need. We have some small format batteries. We have our larger Phi batteries. These come without communication. So these are great for lead acid replacements. These are great for lower cost systems. For customers that are looking for communication and being able to remote monitor, we have our AmpliPhi batteries and our SimpliPhi batteries. The SimpliPhi batteries are coming in at about 5 kilowatt hours, and the AmpliPhi batteries come in just under 4 kilowatt hours at 3.87. So I think I better skip towards the end. I do want to highlight our website. If you do have questions about installing our batteries with other equipment, I highly encourage you to make use of our integration guides. We have integration guides for how to couple our batteries with equipment from other suppliers, charge controllers, AC coupling, DC couplings, Solarx, Schneider. I think there's one for Fronius, Daniel. I mean, we've got a lot of stuff on this website, and so please make use of the installation manuals and the integration guides that are here. So those of you that are installers, I want to encourage you to consider applying to our installer qualification program. Currently, we're offering you $100 per battery that you install as cash back. We do this quarterly. So if you install 40 batteries in a quarter, right, in this quarter, we would be offering you $100 as $4,000 back, right? And so this, you get that just by registering. So if you're join this program, it's free to join. If you join this program, you do that just when you register those warranties. We go through those warranties and send checks based on the number of warranted batteries that you do. So currently we're offering that $100 cash back for batteries. If you're here for NABCEP credits, please send an email to training@simpliphipower.com and let us know how your name appears registered with NABCEP. So if you're looking for that NABCEP continuing education credit, please send us an email. Daniel, I know we're over time. I'm sorry I had to rush everybody here at the end. We're 3 minutes over, but if there are any great questions, I'm happy to stay longer.
Yeah, thank you. The SimpliPhi and AmpliPhi battery we offer has closed loop communication capabilities. It can talk to certain pieces of equipment. What pieces of equipment can it communicate with, and is Schneider battery inverter one of them?
Not yet. So Schneider is on the list, and I've got a Schneider just to the left of me right here that we still haven't quite finished the closed loop communications with, and that's the top of our list right now. So it should be soon, but it's not quite yet. We do communicate very well with, of course, our own Briggs & Stratton inverter and with the Solarcs at this time. We're having some issues with SMA due to a firmware update that they had. So currently we're limited to the Solarc and to the SimpliPhi Briggs & Stratton inverter.
Great, thank you. There's one here. I think Jeffrey was chiming in again about the AC source circuits. He was asking to distinguish the difference between AC modules and field installed micros, because an AC module, there is no DC circuit per the NEC, or rather an AC module is not subject to NEC codes pertaining to the 690. So I think there's some code questions there. And Jeffrey, if you want to email us.
Yeah, so Jeffrey, I don't actually know the answer to that at this point. So email us and we'll get some details for you.
Anthony is mentioning if it's AC coupled and it's a sustained outage, for example, a natural disaster, if the battery goes dead, system is dead until grid comes back on. And there he mentions about Tesla started AC coupling because they weren't originally allowed to do backup. Both Enphase and Tesla have had most of their sales in Hawaii and Australia, where export is limited to the grid.
Yeah, so yes, that is true. If the batteries go completely dead, right? But in most cases, you can set a reserve on your batteries with a low battery cutout, right? And so when solar is available, if you have maintained a small reserve, then you can turn that system back on and have that AC coupled solar producing and charging the batteries again. So yes, you're right. I mean, there are limitations on using with string inverters and with AC coupled systems. There are limitations of getting that solar back, and you don't have that same issue with DC, right? If your batteries go dead with DC coupled solar, the sun comes out, it's not a problem. It doesn't need an inverter to turn on in order for those MPPTs to fire up and start charging that battery. So it's a good example. Thank you.
And I'm not sure how deep we can get into this. Please provide details on grounding of PV modules and batteries for DC coupling.
Okay, actually, this is one that, so there might be regulations on grounding panels depending on where you are. I don't like grounding solar arrays, even the racking. And the reason for that is if you have grounded the racking, any touching the positive wire, any short in the positive wire can produce a short circuit condition or can shock somebody, and it's dangerous. If the array is floated and and most systems are, right, where the PV wire there is no grounding on the system, then you don't have that problem. So you can ground the racking, but do not ground the black or the negative side of your panels to the racking. I hope that answered the question. Daniel, did I interpret that wrong?
Yeah, no, I think what you're doing is you're making a difference between equipment grounding and grounding of current carrying conductors. Very good, yes. Last question, and I think we kind of maybe already addressed this. Say the grid is down and you have an AC coupled solar, and the PV, the AC coupled solar, is producing more power than the house is using. What do we do to curtail that charge? Frequency shifting. I guess they're asking is that if you have more power, then
right, you have to shut the whole system off, and the way you do that is with frequency shifting, right? And you can't do that you can't shut down an individual panel. When you frequency shift, you're shutting down, all of the panels at the same time, assuming you have the same types of panels on your system.
Yeah,
right?
and whether string inverter. And I think that brings up a good point that
Or
we
string
need to make
inverter.
sure that when we are considering AC coupling, when we do show up to somebody's house, we need to make sure that that string inverter or microinverters that are there are new enough, SB 1741, SB, I believe, the new enough inverters so that they can listen to these frequency shifting commands and make sure it's compatible. Email us, training@simpliphipower.com, if you wanted us to vet that inverter to make sure it's capable.
Right.
A last thing is that we are going to email us for your training certificates, or if you want everybody's going to be emailed a recording of this webinar automatically. Thank you, Nathan. That was all the questions we had.
I appreciate that. And if you have design questions and you would like to access one of our engineers to help with your system design, feel free to call. That number is 805-640-6700. And we have sales application engineers, which can help check your particular application and make sure our batteries are a good fit and your design is appropriate. So feel free to reach out there as well. Again, for NABCEP certificates, like Daniel said, email us, training@simpliphipower.com, and we'll get those issued. Thank you for attending today. Appreciate your time, everybody.